All right, time to define dimension one more way. The dimension of a vector space, abbreviated dim of V, or a subspace S, if we want dim of S, is the number of vectors in any basis. So the number of uh, vectors in any basis. So it's the number of vectors that are needed to span that vector space and to make everything else out of a linear combination of them. And they are linear dependent. It's not too surprising. Basically, a classic basis is the axes, the x-axis, the y-axis, the z-axis. Usually we think of those as infinite lines, but just pick a vector on each of the axes and that gives you a basis. And that's what the standard basis for Rn is. Rn is the n-dimensional Euclidean space, and we call the standard basis E for Euclidean, and then we use E, script E for lots of other standard bases as well. And the vectors are E1, E2 up through En, where by EI vector, we mean it has all zero components except for one in the ith component. So here's what it looks like for R4, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Those are the familiar vectors in R3 that we call ij and k if you've seen that before, but we'll call them E1, E2, and E3 here. And they also are the columns of the identity matrix that we've seen already. So notice that in red I mentioned that this is an ordered basis. We write it as a set, and usually sets you can scramble them all around, and if you do, you'll still have a basis. But we want to keep that order, specific order, just like we keep the order for xy and xyz points. We'll keep the order that's given in a basis so that we know what we're talking about when we refer to the first, second, third, and so forth. Rn has many other bases, in fact, an infinite number of them. You can pick any collection of n vectors in Rn and make sure that they're linearly independent. And then you can use them as an alternate way to span the whole space Rn. In fact, we have this 2 out of 3 rule that works for any vector space. So we'll say the vector space has dimension n. Then there's the 3 things that could be true. And the idea is that if any 2 of them are true, the third one is true too. So say you have a set of n vectors, and you could say that they're linearly independent, then you'll know that they automatically span the whole vector space. So here, I'll just write down all the 3 things. If you have n vectors and they're linear independent, then that means that they span the whole vector space. If you have n vectors and they span the whole vector space, that means that they are linearly independent. And finally, if they're linearly independent and they span the whole vector space, that means you have to have exactly n. Now we need a new example. Instead of just working in Rn all the time, this is a new one called Pn. It's the set of all polynomials with degree at most n. So they're not that hard of a function to deal with. We've seen them before. For example, P2 is going to be all the polynomials with degree less than or equal to 2. So here's some examples like x squared, which is a parabola, or 3x squared plus 2, if you want to make it a little more interesting parabola. Or in general, 1/2 x squared minus 3x plus 7. That's like the most complicated parabola that you'll see. It has coefficients for x squared, x, and the constant. And then there are other polynomials with degree less than or equal to 2 that don't even have an x squared term, like the number 5, which is just a straight line, y equals 5, or x minus 1 with slanted line, or 0, another straight line, but it's actually the function that always outputs 0 for any input. They all have degree less than or equal to 2, since degree is the highest power you see. So P is a vector space. It obeys all 8 of our vector space axioms. To add two polynomials, we just put plus in between them and add them up. But what that means is that we could collect like terms. And to multiply a polynomial by a constant, we just put it out front and multiply through the parentheses. So for instance, 3 times the polynomial 3x squared plus 2 plus the polynomial x minus 1. Those are a couple examples from above. Once you multiply through and add up like terms, you get 9x squared plus x, and then plus 6 minus 1, so plus 5. And that's a polynomial in P2. And the zero function is the identity. And we don't have to write a vector on top of it because it is just 1, 0 this time. And you add it to any polynomial and it's 3x squared plus 2. But if you write a vector on top of it, that also is fine because it turns out that polynomials obey all 8 axioms of a vector space. So now we can ask questions about sets of polynomials. Since they obey the axioms of a vector space, we can think of polynomials as being vectors. And then we can ask, is this set x squared plus 3 and x squared linearly independent? That means, back from the definition of linear independent, if we put multipliers out in front and set it equal to 0, in this case the regular 0, since that's the 0 vector in the set of polynomials, then do those coefficients both have to be equal to 0? So we'll expand that, make it c1 times x squared plus c1 times 3, multiply through the parentheses, plus c2 times x squared, set it equal to 0. And combine the like terms, so we have c1 plus c2 times x squared plus c1 times 3 is equal to 0. So this has to be true for all x values. Notice that in polynomials, I'm using x to stand for the variable in the polynomial, like y equals f of x. That means it ranges over the real numbers, and if this is true for all x values, then we can fill in x equal to 0, and we just have c1 times 3 is equal to 0, which means that c1 is equal to 0. It's kind of a familiar feature if you've done, I'll say, Calc 2. Whenever you have two polynomials and you set them equal to each other, you can set the coefficients of the like powers equal. And you can do that by filling in values for x. Like if I fill in x equal to 0, then I have c1 times 3 is equal to 0, so c1 is equal to 0. Then if I plug that in for c1, I have c2 times x squared plus 0 equals 0. And then I get c2 times x squared equals 0. And that has to be true for any value of x. I could pick x equal to 1 and set c2 is equal to 0. So that means we have one unique solution there, and it's linearly independent. Both of those constants had to be 0. So there's a couple of other ways to do that. You could look back at the problem. You could set the powers, the coefficients of like powers equal. So you could know that c1 plus c2 has to be equal to 0, and c1 has to be equal to 0. So then quickly c2 has to be equal to 0.